All right, let's get into this last set of guided practice problems for this unit. And this is where we're going to learn the stoichiometry part of this unit. Now, this is very similar to the stoichiometry that we learned in Unit 8, but there are three different types of stoichiometry problems that we will see. And we're going to go through those three types. The first type is a volume to volume problem. So if we have volume of A, and that's just volume of any gas, we can convert that to volume of B. And we can go directly from volume to volume exactly like we can go mole to mole, which when we go mole to mole, what do we use? We use the coefficient from the balanced chemical equation. And we will look at an example of this in just a moment. But just keep in mind that the way that you go volume A to volume B is exactly the way that you go mole of A to mole of B. This is the easiest type of stoic problem. And again, we're going to go over an example. The next type is when we are at standard temperature and pressure. If we are at standard temperature and pressure, we can use this where it's 1 mole is equal to 22.4 liters. And so if we're at standard temperature and pressure, we can go from volume to moles using the fact that 1 mole is 22.4 liters, because that is the standard molar volume. Now, the last situation is where we are not at standard temperature and pressure. So we're not at STP. And if this is the situation, then you need to be using PV equals nRT. And so these are the three situations in which we will be doing, are the three types of gas stoichiometry problems that we'll be doing. And we're going to look at an example for each one of these coming up here in the guided practice problems. So let's go ahead and take a look here. We're given this balanced chemical equation here. It's the combustion of propane. And first off, I want you to point out, or I want you to notice how all of the reactants in the products are gases. So they're all gases, all right? And I'll be important for a moment here. But let's go ahead and read this first question here. It says, what will the volume be? Okay, so it's asking for a volume of oxygen gas required for the complete combustion of 0.250 liters of propane. Now, this is giving you a volume, and it's asking for a volume. Again, this is giving you a volume and asking for a volume. So, are we at situation 1, 2, or 3? Well, it's giving you a volume, and it's asking for a volume. So, we are at situation 1. We are dealing with the first type of stoichiometry problem here. And so, step 1 is to write what's given to you. So, we have 0.250 liters of propane, which that's going to be C3H8. And we're going to go from liters of propane to liters of oxygen gas. And this is just like a mole-to-mole problem. So again, we can go from volume of one substance to the volume of another substance. And it's just like a mole-to-mole problem where we use the coefficients. And so what is the coefficient for the propane here? It's 1. And what's the coefficient for the oxygen gas? It is 5. And essentially what this is saying is that 1 liter of this will react with 5 liters of oxygen gas. And so notice how we will need 5 times as many liters of oxygen gas. And when you type this in your calculator, you end up getting 1.25 liters of oxygen gas, and this is your answer. So these are the easiest type of problems. Is again, this is where it gives you liters and it's asking for liters. So if it gives you liters and asks for liters, you can go directly from liters of one substance to another using the mole-to-mole ratio. So let's go ahead and do the next problem here. So the next problem says, what will the volume of carbon dioxide be that is produced? So now it's asking for the volume or the liters of carbon dioxide. So it gives us liters of propane and it's asking for liters of carbon dioxide. So this is a liter to liter problem. It's a volume to volume problem. It's the same exact thing. So we have 0.250 liters of C3H8 And it's the same exact setup, except instead of going to oxygen, liters of oxygen, we're going to go to liters of carbon dioxide. And again, we use the coefficients from the balanced chemical equation. The coefficient for propane is 1. The coefficient for carbon dioxide is 3. And when you type that in the calculator, you get 0.750 liters of CO2. And that is with sig figs. So again, this type of stoichiometry problems are really easy. Again, if it's giving you liters and asking for liters, you can go directly between the two using the mole-to-mole ratio. All right, let's go ahead and take a look at this next problem here. This says solid calcium carbonate, also known as limestone, will decompose upon heating to produce solid calcium oxide, which is also known as lime, and carbon dioxide gas. How many grams, okay, so there it is, how many grams of calcium carbonate must be decomposed to produce 5 liters of carbon dioxide gas at standard temperature and pressure? And so what I want to point out with this one is giving us liters or giving us a volume, and it's somehow wanting us to go to grams. So the first thing I'm going to point out is, notice how it is not situation 1, because situation 1 is a liter to liter problem. But this problem here is asking liter to gram. So we're not at situation 1. So are we at situation 2 or situation 3? Well, notice this part here. Notice how it says at STP. So we are in situation 2. So this type of problem is going to be at standard temperature and pressure. We will end up using 1 mole is equal to 22.4 liters at some point. And so let's go ahead and get started with mapping out this problem here. The first thing we need to do is write a balanced chemical equation. All right, so it's got calcium carbonate, and it decomposes into calcium oxide plus carbon dioxide. And this particular problem, or this particular balanced chemical equation, this is already balanced actually. So it's a 1-1-1 coefficient. So all the coefficients are 1 in this situation. Now, notice how this is going to be a solid. Okay, this is a solid. This here is a solid as well, and this is a gas. So this here, we will be able to use a volume on that one just because it's a gas. Notice how these other ones, which are solids, those will never give us a volume, and they'll never ask for a volume because they're not gases, they're solids. All right, so let's go ahead and look at what's given us. So we're given liters of carbon dioxide. Okay, so we're given liters of carbon dioxide. And we're trying to get to grams of calcium carbonate. And something to keep in mind is, notice how we're starting with carbon dioxide and we're trying to get to some quantity of calcium carbonate. So that means that we somehow need to go from mole to mole. We need to go moles of A to moles of B. So notice here, since we're at standard temperature and pressure, we can actually convert from liters of carbon dioxide to moles of carbon dioxide. And once we know moles of carbon dioxide, we can actually convert it to moles of calcium carbonate. And once we have moles of calcium carbonate, we can go to grams of calcium carbonate. What I will say is, in this unit, this part is the new part. The liters to mole part is the new part. This is what we learned last unit. And so the connection I'm wanting you to make is that if we can somehow get this to convert to moles, we can then use what we've already learned in the past to then go from moles of A to moles of B to grams of B. Now remember what we learned in this unit, where 1 mole of any gas at standard temperature and pressure is going to be 22.4 liters. And so this is what we're going to use to convert from liters to moles. And so we have 5.00 liters of CO2. We're going to go liters of CO2 on the bottom because we're canceling out units, and we're going to go to moles of CO2. We're then going to put moles of CO2 on the bottom, And we're going to convert moles of CO2 to moles of calcium carbonate. And just to remind you, this is the point right here that we've learned last unit. So this is what we learned last unit. So from here on out, it should be familiar. And we're going to go moles of calcium carbonate to grams of calcium carbonate. And so the moles cancel, these moles cancel, and now we're left with grams. Now, when we convert between moles and moles and liters, when we convert between moles and liters, we know 1 mole of any gas is going to be 22.4 liters of that gas. And when we convert between moles of one substance and moles of another substance, so when it's a mole-to-mole conversion, we use the coefficients from the balanced chemical equation, so these coefficients right here. Notice how they are all A1 in this situation. And then when we convert between moles and grams, we know that 1 mole of any substance is equal to the molar mass in grams of that substance. And so we know that 1 mole of this, and calcium is 40, carbon is 12, oxygen is 16 times 3, and all of that adds up to 100. So when you add all of that up, it adds up to 100, and that's the rounded molar mass using rounded numbers from the periodic table. And all you have to do is type that in the calculator, and when you do that, you get 22.3 grams of calcium carbonate. All right, so this one's not too bad either. All right, so this one's not too bad. Notice, again, we're starting with liters of carbon dioxide, and when in doubt, just try to convert everything to moles and convert through moles, because remember, we go from moles of one substance to moles of another substance through moles. So we go from one substance to another substance through the mole ratio. All right, let's go ahead and go on to the next one here. So this one we have this problem where it's asking how many liters. Okay, so it's asking for a volume. All right, so how many liters? And it's giving us a temperature, it's giving us a pressure, and it says how many liters of hydrogen gas at this temperature and pressure are needed to react completely with this many grams of tungsten. So this, again, is not a liter-to-liter problem. This is a liter to gram problem. So we somehow need to go from liters to grams. And this is going to be liters of hydrogen gas. And we're trying to get to grams of the tungsten oxide. So let's go and take a look here. It's not a volume to volume. It's not a liter to liter problem. Now, is it at standard temperature and pressure? Well, standard temperature is equal to 0 degrees Celsius, and then the standard pressure is equal to 1 atmosphere of pressure. Notice how that is not the pressure or the temperature that we are at. It's not the pressure or the temperature that we are at. Instead, we are at a different temperature and pressure. So because we are not at standard temperature and pressure, it's not going to be this. Instead, we are in this situation right here where we're somehow going to have to use PV equals nRT. So let's go ahead and set this up. So we have PV equals nRT. We always have R. The problem gives us T. The problem gives us P. And it's looking for V. So what is the one thing that we're missing? What's the one thing we're missing to solve for V? Again, the problem gives us the pressure right there. It gives us the temperature. We always have R. What's the one thing that we're missing? The one thing we're missing is moles. So how do we get to moles of hydrogen gas? Well, notice how we have grams of tungsten oxide. And we can go from grams of tungsten oxide to moles of tungsten oxide. Again, this is what we've been doing almost a whole year, going from grams to moles. And then once we know moles of one substance, we can convert it to moles of another substance. And then once we know the moles of hydrogen gas, we can then just plug it into there. And so this is the way in which we're going to solve this problem. So again, we're trying to solve for volume. That's this one right here. That's what we're trying to solve for. It's giving us pressure. It's giving us temperature. We just do not have the moles, but we can do this right here to calculate the moles of hydrogen gas and then plug in the moles of hydrogen gas to this. So let's go ahead and do that. Okay, so we are given 875 grams of tungsten oxide. We can go grams of tungsten oxide to moles of tungsten oxide. And then we can go moles of tungsten oxide to moles of hydrogen gas. This first fraction, when we go between moles and grams, we know that 1 mole is equal to the molar mass. And the molar mass that you get from the periodic table, when you add them all together, you have 1 tungsten, you have 3 oxygens, is about that. When we go mole to mole, we can use the coefficients from the balanced chemical equation. So the coefficient for tungsten oxide is 1, the coefficient for hydrogen gas is 3. And then all we have to do is type this in our calculator. And what we get is 11.3 moles of hydrogen gas. Now, this isn't our final answer, but that's the final answer for this first part. Now that we have the moles of hydrogen gas, we can then take these moles of hydrogen gas and now plug it into PV equals nRT. And so we know the pressure is 0.980 atmospheres. We are looking for the volume. We just calculated the moles. R is a constant, which is 0.0821. You find that on your equation sheet, the second page in your booklet. And then T is, well, we're given Celsius, so what do we have to do to the Celsius? We have to take the Celsius and add 273 to make it Kelvin, and you end up getting 308. And that's our setup. And now all we have to do is solve for V by dividing both sides by 0.980. 0.980. These cancel out. And we are left with this setup here. All we do is type that in our calculator. And when you do that, you get the volume is equal to 292 liters of hydrogen gas. And that's your answer. And we put a little smiley face because we're happy that we're done. All right, so let's go ahead and real quick take 30 seconds here to recap what we just went over. First, we did a volume to volume problem, the easiest problem. This is the type of problem you want. If you have liters and it's asking for liters, you can go liter to liter using the mole to mole ratio. The next one we have is at standard temperature and pressure. It's also not too bad. Just remember that you go from liters to moles using 1 mole is 22.4 liters. Then it just becomes a normal stoichiometry problem where you go mole to gram. And then we have this last one. In this situation, we're given grams and asked to calculate liters, but it's not at standard temperature and pressure. What you do is you convert the grams of the one substance all the way to moles of the gas that you're trying to find. Then you take those moles and you plug it into PV equals nRT. And then you solve for your volume. And that is those are the 3 types of Stoic problems that you will see on the exam. And we'll go over some more practice problems. We'll practice this several times before the exam. If you have any questions, feel free to email me or come to class with questions. Have a great day.